Okay, so I'm back in the classroom. So let's pick up, let's do the next unit, area. So the first thing we want to talk about is a unit square. So we know what a square is, and the question is what's a unit square? A unit square is a square whose dimensions are 1 unit by 1 unit. For example, so the area, yeah, so it's 1 unit by 1 unit. So maybe it's 1 centimeter by 1 centimeter, 1 foot by 1 foot, and that's a unit square. So now we can define area as the number of unit squares that fit or are contained, let's see, are contained in a figure. So the first question is, how do we find? First of all, does a figure have an area? So, for example, if I put this on the board and I would ask you, does that figure have an area? And you would say, I would ask you, does it have an area? And you say, yes, it has an area. I would ask you, can you prove it? Well, I want you to think about it for a second. How can you prove that this has an area? Let me turn this a little bit. Yeah, can you prove that this figure has an area? And the answer is yeah, because I can put a square here, and I can put a really big square around here. And so I know that this weird figure is somewhere between this small unit square and this big unit square. So I know the area exists. So the area exists. So our next question is, how do we find the area? Now, if you think about your history there, you've studied this before, when you were in like third grade, fourth grade, your teacher would have you draw a figure, but like on graph paper. And so you take the figure, there would be a piece of graph paper, and it would look like this, you know. So can you see the blue figure? Well, let me make it red so you can see it. So the figure was put on graph paper, right? And then the teacher said to find the area, because graph paper is made of all these unit squares, they would say count the number of unit squares in the figure. And you'd be like 1, 2, 3, 4, 5, 6, 7, 8, and you would say the area is 8 unit squares. Unit square. So for example, maybe it was like 8 centimeters squared because you counted 8 of the little squares. And that was fine for like rectangles, but it became a little more problematic when you started to do triangles, trapezoids got weird, and then the area for circles, which still is, that's the idea. The area of a circle is the number of squares you can stick in it. It just got messy, so you couldn't do that anymore. So you came up with some formulas. So let's just go through those formulas quickly. Let's talk about area, because it's geometry. Sorry, let me close my panels. So let's talk about the area of a rectangle. Now the rectangle was easy because it was very clear that there was a base and a height, and it was very clear what the base and the height were. And and it was much easier. At some point, you said, "Oh, you know what? I don't need to add up all the squares. All I need to do is just define a base, and then find the height, and then so the area of a rectangle is base times height." Now, sometimes you say length times width, but I want to keep it with base times height. Now. What about a rectangle is the base and height is very defined. What are parallelograms? So let's take a look at the parallelogram. We know the parallelogram, we kind of drew it like this, right? And so the question is, what is the height? I mean, the base is the base. This is the base. The question is, where is the height? And we know the height is the altitude. So so the distance between the bases, this is the height. Or, you drop it down like this. So this is the height. The height of a parallelogram, any parallelogram, your rectangles, your rhombus, your square, is the distance between what you call the bases. It's the distance between the parallel bases, right? So sometimes what I don't want you doing is, so the mistake that some kids make is that, this is a mistake, right? The mistake is that some kids will see something like this. I really should be using a ruler. And the teacher will say, fine, the sides are 10, 10, and 8, 8. And then some kids will say, oh, that means the area is 80, centimeters squared. Wrong. That's wrong. This is not the height. It's just the side. But you have to figure out this altitude, that is the height. Once again, the distance between the bases is the height of the parallelogram. Good. Let's continue. The area of a triangle. Let's see, the area of the triangle. Well, that's easy. Once again, we know that, so we started out with a right triangle, right? But if you think about a right triangle, it's just kind of like half a rectangle or a rhombus. So we knew the formula. We have the base, and we have the height. So we know the area of a triangle is 1/2 base times height. Now, in this year, we moved away from right triangles. So we kind of got, triangles that look like this. And so if we drop, once again, I don't know the angles, but we said that's no problem. As long as you define the altitude, which is the base, and we know that this is the height of the triangle, we can still use the formula. But once again, you have to be given the height. So in the early problems in this unit, you're given the height, but as we moved on in the year, we have more advanced methods. And then through trigonometry, and then we saw in trigonometry, any triangle, if you have, A, B, and then angle C, we knew it was 1/2, 2 sides, and the sine of the included angle. So that's where we took it this year. So once again, all these formulas, it's the number of unit squares that fit inside these shapes. That's the geometry. And the idea is, if you think about it, that's why when you try to find the area of a triangle, that's why the numbers get kind of the fractions show up, because you're trying to fit squares in here, and they don't fully, they kind of don't fully fit. And that's why there's half. Let's move on. What was the next shape we looked at? Well, all the parallelograms. So this includes the rectangles. This also includes the rhombus. We'll get to that in a second. Given a base and a height. We'll get back to that in a second. What's the next shape we're interested in? Trapezoids. What is the area of a trapezoid? Well, I'm not going to go through that. I'm assuming that in previous years you've covered this. Sorry, let me jump on. The area of a trapezoid. Trapezoid. Well, we studied trapezoids. Please remember the English and the British have different words for that. We studied the trapezoid. We know that the two bases were parallel. They're not equal. And we have the two legs. Maybe we have a right trapezoid, isosceles trapezoid, nothing special trapezoid. Once again, like over there, the height of the trapezoid is the distance between base 1 and base 2. In this case, they're not equal, but still the same idea. And so we know from our previous years that the area is 1/2 the height times the sum of the bases. Now, I'm not going to go through the proof, but it's very easy. What you would do is you would break up the triangles into 2 triangles and a rectangle, and this would be base 1. Let's call this, so this is B1. Let's call this B1. Let's call this A, B1, and C. And then the idea is you find the area of the triangle, you add it together, and you would get, the sum of the bases times the height times 1/2. That's the formula. And it's just very strict. Plug the numbers in. What's next? The next thing is kind of cool. How do we find, the next thing is kind of cool. We want to find the area of the kite and the rhombus. And this is awesome. I love this formula. Now, once again, you could be given a rhombus, you could be given the base and the height. But let's say but this is really cool. We can find the area based on the diagonals. So we're going to take our rhombus. What do we know about our rhombus? Once again, you're told you have a rhombus. So you know that the sides are all congruent. You also know the diagonals bisect each other. And you also know that the diagonals are perpendicular to each other. So you notice, you're like, hey, Mr. Adler, we have 4 congruent triangles, right? So I can find the area easily because they all have the same height and base. It's right triangles. It's a gold mine. It's perfect. So let's call the first diagonal. Let's call the first diagonal D1, and therefore this height will be D1 over 2. Let's call the second diagonal D2, and therefore each of these parts is D2 over 2. Therefore, the area of one of these triangles is equal to 1/2 the base, which is diagonal 2 divided by 2, times the height, which is diagonal 1 over 2, and that's equal to D1. I'm going to put D1 first, sorry. D1 over D2 divided by 8, but I don't have 1. It's 4 of these. So times 4 gives me the area of a rhombus and a kite is equal to 1/2 the lengths of the product of the diagonals. Awesome. Kind of cool, right? Nice. Now, so we've done all our shapes, right? We've done everything, right? So, are we done? No, we're not done. Let's continue. So first, we're going to take the area, and so I haven't done an example, but I just want to get through the video. So now we know how to find the area of every single shape, almost every single shape we've done. We still have the circles, but we also have the regular polygons. I should be able to ask you, what is the area of a hexagon? Yeah, the area of a hexagon, or an area of an octagon, given a couple of conditions. So first of all, I want you to watch the video right now of how to use geometry to actually make a hexagon, an octagon, or any n-gon. Okay, so I want to show you how to make a regular polygon. So what we're going to do is we're going to go to circle. We're going to put a point in the center. And what then we're going to do is we're going to make a circle. So let's just bring a circle out. It doesn't matter the size, right? I'm going to put this over here. Nice. So we have the circle. Now let's make a hexagon. So a hexagon has 6 sides, but I want a regular hexagon. So what we're going to do is first, I'm going to plot a point up here. Let's put it right near. I don't want it on top of B. So actually, let's go to move. Let's go to the calculator. I'm going to hide B. Nice. So let's go back. We're going to put a point anywhere on the circle. And then the idea is I want it equally spaced around the circle. And so sometimes when you're asked, like, what's a circle? Your first response is, oh, it's 360 degrees. Well, I'm going to take 360 degrees and divide that by 6. 360 divided by 6 is 60. So I'm going to rotate C about A at 60 degrees. So let's go to transform. We need more. Sorry. We need more. Scroll back down to transform. We're going to rotate around a point. So I'm going to take C, rotate it around A, 60 degrees. Let's do that again. Rotate C about A, 60 degrees. Let's do it again. Rotate C about A, 60 degrees. Okay. Let's do it again. C about A, 60 degrees. Okay. I think we could do it one more time. Rotate D about A, 60 degrees. And I think we got it. Now, let's connect these points. So let's go to, let's see, I want segments. So let's say I want C to C prime to C double to C triple to D. I guess they ran out of knots. D to D prime, and then D prime back to C. And you have a regular polygon. Let's hide that circle. And you have a regular polygon. And that's how you make a regular polygon. Now, a couple of things. Actually, let's bring the circle back because we need some information. What happened to my circle? Let's see. I'm going to bring my circle back. I'm going to connect. Am I still on segments? Yeah, I'm going to connect A. I'm going to A to C, and these are known as the radii. It's like the spokes. Now, what we're going to the small unit, finding area of any regular polygon. This is the idea. We're going to take our regular polygon and break it up into a bunch of isosceles triangles. Some of them might be regular, and the idea is we're going to find the area of all these triangles. Like AC, this is known as the radius of the polygon, and then there's other thing. I'm going to find the mid. Whoops, sorry. Let's undo that. I'm going to go back to circle start. I'm going to find the midpoints of. You know what I'm going to do first of all? I'm going to move C around a little bit. Let's see. Move. Sorry. Get rid of A. I'm going to go back here. I'm going to move. I'm going to just move C around a little bit. Nice. So all these segments. Now I'm going to draw. I'm going to first find the midpoints. So let's see. Let's go. Let's see. Let's find the midpoints of the segments. And then what I'm going to do is I'm going to draw another segment. A segment from A to E, and this is known as the apothem. Let's put some text in there. So, I'm going to write it on the board. So AC, AD, that's known as the radius of the polygon, and AE is the apothem. And you can see we can find the area of the triangle. First, we have the length of the base times the height, or the apothem times the side of the polygon, and then we multiply that by 6. And that's the idea of finding the area of any regular polygon. Okay, nice. So let's think about, once again, let's just quickly review the video. We had a circle. So once again, area of regular polygons. So first of all, let's just, we talk about a regular polygon, all the sides and angles are congruent. Because once again, a rhombus has all congruent sides, but all the angles are not congruent. The square is the regular polygon. The equilateral triangle is the regular polygon. So what we did was We took a point, we made a circle, right? And then what we did is we equally spaced that over we took 360 and divided by whatever n gone. So for example, in the movie, I made a hexagon. So a hexagon has 6 sides. I took 360 divided by 6, and I spaced the points at 60 degrees. And then we connected the lines. I know it's a horrible picture, but you can do this on your own. And so we created a regular hexagon. Then what we did was we connected the center of the circle to the vertices of the polygon. This is known as the radius. It's like the spokes of a tire, like when you go riding on your bike. This is the radius. And then we defined the height from the center, the altitude, to the side as something called the apothem. And now we have, and once again, let's think about this also. So the question is, well, you only made one triangle, Mr. Adler. Well, no, because let's think about this. Depending on how many, on your n gone, we created 6 or n of the same triangles because the radius of a circle are all congruent, and the lengths of the sides of the hexagon are all congruent. Which means all I have to do is find the area of one of those triangles and then multiply by, in this case, 6. So, let's see. Let's see. Now, the question is, what is the area of this triangle? Well, first of all, what's the length of the side? Well, let's see. The length of this side is the perimeter divided by 6. Okay, so the area of one triangle is 1/2 the base times the apothem. So what's the question is, what is the area of the entire thing? You go, fine. You say, fine. Therefore, the area is equal to 6 times 1/2 the perimeter divided by 6 times the apothem, and you get this really interesting formula. The area of a regular the area of any regular polygon is equal to 1/2 the apothem times the perimeter. So in the first couple of problems, you're going to be given the apothem and the perimeter, and from those 2 pieces of information, you can find the area of a regular polygon. That's kind of awesome. Let's move on. So the next thing is we want to bring in what happens, and we saw this with dilation. So let's think about a week ago the idea of dilations. So what happens when you, to the area, the perimeter, and now the area when you dilate a figure? Good. So let's talk about area of similar triangles. Area of similar triangles. It's very straightforward. So let me get a new passage. This one's running out. So in the last unit, we took like a 3, 4, 5. And like we dilated it to 30, 40, 50. And so the idea is the ratio was like, maybe we said the ratio was like 10 to 1. Actually, let me change that. So let's see, we started with a 3, 4, 5 and expanded to a what? An 18, 24, 30 figure. And so the scale factor was, let's call, it was like, A to B, which was 3 to 18, or like 1 to 6. So the original figure was 1, the large figure was like 6 times it. So the question is, what's going on with the perimeter and the area? Well, let's see. The perimeter here is 712 units. Let's use centimeters. And the area is 1/2 the base times height, or 6 centimeters squared. What's going on here with the new scale factor? Let's see. So the perimeter here is 18 plus 24 is 42. This is 72 centimeters. And the area here is 18. Let's see. Let's check this out. It's 1/2 times 6 times 3 times 6 times 4. So this becomes 1/2 3 times 4 times 6 squared. So this is the point I want to make. So once again, the perimeter, the perimeter is in a ratio of 1 to 6. Oh, this is bad time. So we see here, the perimeter to perimeter. So we have 12 to 72, or 1 to 6. Let's compare the areas. The area is, it's 6 over 6 times 6 squared, which is 1/6 squared. And that's the idea of area. So for example, let's use some examples. This is kind of interesting. So for example, if the ratio is 5 to 7, the ratio of perimeters is 5 to 7, but the ratio of areas is 5 squared to 7 squared. Right? That's kind of interesting. Let's do an example. Let's take an example. So we have a triangle here. How are we doing for time? Oh, getting close to ending. Here, so we have a triangle here, and the base is 2. And we have a similar triangle. The base is 5. Okay. Now we're told that the perimeter of the smaller is equal to 20 centimeters, and we're told the area of the larger triangle is equal to 30. The perimeter of the larger is 20 centimeters, and the area of the smaller is 30 centimeters squared. And what you're asked to do is find the perimeter. Find the perimeter of the smaller and find the area of the larger. And so this is very straightforward. The perimeter of the smaller compared to the perimeter of the larger is equal to 2 to 5. Therefore, the perimeter of the smaller is 8 centimeters. What's going on here when we find the area changes a little bit. We know that the area of the smaller is 30 over the area of the larger is equal to, it's not 2 to 5, it's now 4 to 25. And so with manipulation, you get the area of the larger is equal to 187.5 centimeters squared. So that's the idea of the comparison, and we'll see with the volume unit is that the ratio is not like A. So the perimeter is A to B. Area, the ratio is A squared to B squared. Did I write that down? No. So this would be A squared to B squared. That's area. And then for volume, we're going to see it's actually a cubed to b cubed. Good. Last little unit before we're done. What is the area of a regular n-gon if the perimeter is known? This is kind of interesting. You'll like this. So can we determine the area of an n-gon if we have its perimeter? And the answer, because generally you can. Like if I tell you the perimeter of a triangle is 20, you can't figure out what the area is. If I tell you a rectangle has a perimeter of 15, like you don't know what the area is. You can come up with some ideas. The question now with regular polygons is that if I give you the perimeter, you can find it. So find the area. So find the area of an octagon if the perimeter equals 80 centimeters. Let's see, 80 feet. So let's see, let's break this down. So we have our octagon. We have our center. I'm going to look at one triangle. So the perimeter is 80, therefore each side equals 10 foot. Okay. So you say, Mr. Adler, how do I, that's great. So I have this one triangle. I know there's going to be 8 of them, but I don't have the apotheosis. The apothem, well, you can figure something else out though, because this circle here is 360 degrees. And since they're all equal, this angle here, 360 divided by 8, is 45. What I'm going to do is I'm going to take this triangle out. So I have 10 feet. I have an isosceles triangle with a 45-degree angle up here. But you know what I'm going to do? I'm going to drop an altitude. We know from OR you're studying that an altitude in an isosceles triangle bisects the base and bisects the vertex. Well, the question is now, how do we find this apothem? Well, we have an angle, we have an opposite side, and an adjacent side. Trigonometry. The tangent of 22.5 is equal to 5 over A. And so, all we need, so now we have A is equal to 5 over the tangent of 22.5, and the area of our octagon is equal to 1/2 times the apothem times the perimeter. And you can come up with your own formula, but the idea is, once again, if you have a regular polygon, and you know the perimeter, you know you have a side and you have the angle, drop the altitude, use the tangent ratio to find the apothem, and you can find the area. And I think that's kind of cool. I think that's awesome. And am I done? Are we done? Yeah. How about this? Fine. Last example. How are we doing for time? Hey Siri, what time is it?
It's 8:54 a.m.
Perfect. Next question. Find the area of a pentagon whose perimeter is 70. Let me erase this. Find the area of a pentagon whose area is 70. Whose perimeter is 70. Find the area of a pentagon, a regular pentagon, whose perimeter is 70 meters. Take a second to figure that out. Okay, we're back. right? We have a pentagon. Let's see. Not the best figure. I'm not the best artist. Draw in the center as if it's around the circle, right? You don't have to draw the circle in. You can if you want to. I'm going to draw in one triangle. So I know there's 5 congruent triangles. So I know the pentagon has 5 sides. So first of all, each side is equal to 70 divided by 5, which is, what's 70 divided by 5? 14. And the question is this angle here, what is theta? Theta is equal to 360 divided by 5, which is, well, let's see, 360 divided by 10 is 36. So 360 divided by 5 is 72. So I'm pretty good here. So I know that if I drop the altitude, I have, this is 36 degrees. I know that this is 7. And so I can find the apothem. Either you redo it, you can redo SOHCAHTOA every time, or you can kind of remember that A is equal to 7 over the tangent of 36, and therefore the area is equal to 1/2 the apothem times 70. And so what do we have here? 35 times 7. Hey Siri, 35 times 7.
35 times 7 is 245.
245 divided by the tangent of 36. And whatever that comes out to, that's the area of your triangle. Nice.